Hello everyone, my name is Yijun Yang. I'm a PhD candidate of the Chinese University of Hong. I shall be speaking today about our paper, What You Think is Not What the Network Infers, detecting adversarial examples based on the semantic contradiction. Let's move to the introduction session. Deep learning-based systems have achieved great success in numerous long-standing machine learning tasks, with the broader development of DNNs in various mission-critical applications like the medical diagnosis and the autonomous driving, etc. Their safety have become public concerns. In these applications, incorrect decisions or prediction would result in catastrophic financial damage or even life losses. However, DNN-based systems can be easily fooled by adversarial examples. Adversarial examples are yielded by adding intentionally designed perturbations to the input. This anomalous input could deteriorate the performance of the DNNs. We think the adversarial examples are good aspect of security to work on because they present a concrete problem in AI safety and can be addressed in the short term, and because fixing them is difficult enough that it requires a serious research effort, so we'll need to explore many aspects of machine learning security to achieve the final goal of building safe, well-distributed AI systems. Depending on the attacker's knowledge, adversarial attacks can be classified into three categories: the black box attack, white box attack, and adaptive attack. The black box attack, where the adversaries have no access to either the detailed information of the target model or the defense mechanism, but can query the model. In the white box setting, the model architecture and the parameter are exposed to the adversaries, but the defense mechanism is kept confidential. And in the adaptive attack setting, the adversaries have full knowledge of both the target model and the defense mechanism, and they could craft attacks accordingly. So our work will mainly concern the more challenging scenarios, that is the white box attack and the adaptive attack. According to the definition of AE, we deduct two objectives an AE needed to fulfill simultaneously. One is that the adversarial example should cause DNN to make a wrong prediction. The second one is that the AEs should be indistinguishable from its source image. The first item ensures that the impaction of AE samples, while the second objective avoids AE being easily identified. Formally, we summarize the intrinsic feature of AE as the following corollary: that the AE's visual semantic information contradicts its discriminative features extracted by the DNN under the adversarial attack. This figure illustrates this corollary, that the clean input and the correct AE appear almost identical to our humans. However, the DNN model is activated quite differently in the feature space, thus predicting the clean samples as this predicted results and the AEs as the speed limited 80 kilometers per hour sign. The DNN-based image classifier performs the complete nonlinear mappings from the high-dimensional input image space to the low-dimensional feature space. Especially considering that DNN models are constructed with limited training examples, the multi-to-one mapping from DNN models leaves many loopholes for attackers to generate possible AEs that are similar to the clean image in the input space, but differ significantly in the feature space. However, if we project the inference result of the DNN model back to their input space, the contradiction within category 1 can be reflected in the image space. We could then compare this with the original input and at the same space as shown in this image. To perform semantic comparison at the input space, we propose ContraNet, which employs an encoder to capture the low-level features of the input image and feed it together with the inference results of the DNN model to a generator. The semantics of the thick image could conform to the DNN model's output, like the semantics of the thick shown in the right part of this figure that is faithful to DNN's prediction result. We can then easily tell the difference between the AE input and the thick image and use it for AE detection. To further demonstrate our motivation, we empirically show some cases in this figure where the thick image's semantic information is highly dependent on the inferred results from the classifier. To be specific, given input image in the first column, we generate thick images in other columns by varying the label, as shown in the top. Such procedures mimic the semantics changes caused by the AEs at the feature space. As can be observed, ContraNet faithfully reconstruct the thick images when the label is consistent with the input image's semantic information. However, when the given label contradicts with the input image's semantic, the generated thick image could be pretty different from the input image. As for the implementation, the proposed ContraNet design containing an encoder, a conditional generator, and a similarity measurement model. We employ an encoder to embed the features of a specific input image as a latent vector. The encoding step can be seen as a transformation process from an image domain to a high-level latent vector domain. After that, the latent vector containing the specific information with respect to the input image is fed to the generator through its input layer, and the generator is used to generate the input image's projection wherein, which is consistent to the predicted label while considering the low-level feature provided by the encoder. The idea of the similarity measurement model aims to further improve the detection performance of ContraNet by learning a suitable similarity metric. To realize the detection mechanism of ContraNet, the thick image's semantic information should significantly correlate to classifier's predict label Y. To enhance the influence of Y on the thick image's semantic meaning, we adopt the conditional batch normalization technique on conditional GANs generator, which in conditional batch normalization, Y directly influence each batch normalization layer's mean and variance parameters. Therefore, the Y's impaction can spread to generators' deeper layers. For the discriminator part, we employed conditional projection layer technique. This projection structure enables high-quality class information transformation. One requirement of ContraNet is that given a consistent pair of Y and X, the thick image X prime should be similar to X. To this end, we developed an encoder to summarize the input's low-level features to the latent vector Z and send Z to generator's deeper layer. To further ensure X prime is faithful to its corresponding input image give a consistent label Y, we employ an auxiliary discriminator d2 to determine if the thick image A is close to its corresponding input image X. We design a similarity measurement model to distinguish adversarial examples from clean images. We make the judgment from 3 different perspectives. The proposed deep metric model DNN provides similarity judgment by comparing a hierarchical distance between X and X prime. In contrast, the SSIM model provides a pixel-to-pixel similarity judgment. Further, we apply a DIS model to reject a sample according to the quality of its thickness. The insight of this DIS model is that if the given label does not match a sample's semantic meaning, the thickness will appear more unrealistic than the thickness generated with the consistent label. These 3 rejectors work in a tandem way where any rejection of the 3 leads to a final rejection. Table 1 summarizes the performance of our ContraNet and the baselines on clean samples by fixing the threshold at LPR 5%. As can be seen, the accuracy decrease caused by ContraNet is at most 4.5% across 3 data sets. Compared to baselines, ContraNet causes little impact on the original accuracy, especially when compared to methods requiring retraining the classifier like the RR method and the trapdoor. Under white box attacks, ContraNet maintains a high robust accuracy across a variety of attacks and data sets, as shown in the table below. This attack agnostic property is thanks to ContraNet's detection mechanism. By using the semantic contradiction, ContraNet identifies AEs without the need for classifier knowledge or assume the attack types. Consequently, ContraNet is more general than non-semantic based. Then we try to break our ContraNet using 3 types of adaptive attacks. The first 2 adaptive attacks are based on the public known strong iterative attacks, PGD and CW. To further evaluate ContraNet's robustness, we employ a recent adaptive attack benchmark orthogonal PGD, which focuses on breaking detection-based defenses. It is critical to choose the proper loss function for adaptive attacks. On the one hand, an adaptive attack aims to bypass the detector and fold classifier at the same time. On the other hand, an overly complex loss function will complicate the optimization process, resulting in a failure attack. Therefore, the attacker may not consider all the loss items for the defense schemes, but instead find its weakest point and break it. This slide shows ContraNet's performance against adaptive PGD and CW attacks. As shown in this plot, the weakest point of ContraNet varies with different loss items, indicating the objective function design works. This figure exemplifies several attack instances. As perturbation goes larger, AEs can bypass ContraNet tend to have much weakened adversarial semantics or looks more like their target classes. In addition, even under the most powerful CW attack, ContraNet still keeps robustness to a certain degree. This slide shows ContraNet's performance under orthogonal PGD attack. As can be seen, ContraNet outperforms for SOTA detection-based defense under both auth and select attack settings. Thank you for listening.